All right, good day, everyone. Today we're going to be focusing on, in this lesson, is going to be graphing out trig functions. And the key thing I want you to understand is, in today's lesson, we're going to go pretty slow with it. We're going to kind of build up step by step, understand what each value does. Now, as we get past this, can you kind of skip ahead and do things a little bit quicker and kind of jump to certain aspects? Absolutely. It's kind of one of the things that we're going to kind of grow on, but we have to understand how these values are affecting it and then build off of that, especially when you start getting like an amplitude, a period, and a phase shift all together. Okay? So first and foremost, let's talk about this. We have 3 sine of x minus 1. Before I do anything, let's label what we have currently. Well, in this case, based off of my equation, which is typically y equals a sine of b times x minus c all plus d. Based off the transformations I currently have, I have an a and I have a d, right? A is the 3 in front, and then because I don't have parentheses around the x, there's technically nothing on the inside, so that value on the outside is technically that minus 1 should be my plus d. This should tell me right off the bat that we know that we have an amplitude, that a value of 3, and we have a vertical shift of up 1. Now, that's kind of the first step, just understanding those values. From there, let's start to build up how a sine function will look. So in this first graph here, in this first one, I'm just going to graph a single period of sine, okay? So in this first graph, I'm going to graph out y equals sine of x, because I want to be able to build up and truly understand how is this going to change from what I have currently in the equation from the original. So the original sine equation, if I make these intervals of 1, would start at 0. At pi over 2, I'd be up at positive 1. At pi, I'm back down to 0. At 3 pi over 2, I'm at negative 1. And at pi, I'm back to 0. So one period of pi looks like this. Now, let's start to talk on how this is going to change. Before I do that, we do need to understand one small concept. Based off what we have in the equation currently, our period is not going to change. So we know we have a period equal to 2 pi. So that value should stay the same. And I don't have a phase shift or a left or right movement. So I know the graph isn't going to be moving left or right, or it's not going to change the actual period of the function. So now let's start to build up based off of information. The next thing we're going to add is our amplitude. What would happen if I apply a 3 sine of x? Well, the idea of an amplitude is it actually is going to tell you how far up of a stretch your max and your min are going to become. So if you consider this idea of sine, our maximum and minimum was at 1 and negative 1. Forgot to write that there. Well, if I have an amplitude of 3, now that value is just going to go up to a positive 3 and a negative 3. So now these coordinates are particularly going to move. But the key thing to understand is that it's not going to affect the values that are originally at 0. It's only going to affect my max and my minimum values by stretching them to that new amplitude. So this value is now going to become, starting at 0, instead of 1 at pi over 2, it's going to be positive 3. Back down to 0. At 3 pi over 2, it's going to be at negative 3, and then back to 2 pi, giving me a graph that currently looks like this. So notice how my values really aren't changing. Okay, I still have those 5 coordinates that I focus on, knowing that sine starts at 0, and then it goes from to 1, back to 0, to negative 1, back to 0. So that amplitude is just affecting that original value. So for the last one, let's put it all together. Now we have y equals 3 sine of x minus 1. Which I just realized this all the way at the beginning here. For those of you who probably caught it earlier, this is actually going to go down 1 unit. My apologies. Okay? So now if we have a down 1 motion, if I look at this, I'm going to take this value here and I'm going to shift all of these coordinates physically down. So now while the amplitude only affects my max and my min, this value is going to affect all of the coordinates. So now what I can do is take all of these coordinates from my second graph and shift them all down 1. So this value would be shifted down 1 to start at -1. My original max or my new max after the amplitude change would shift to become at +2. At pi, I'm at -1. At 3 pi over 2, I'm at -4. And at 2 pi, I'm back at -1, giving me the graph that looks similar to this. And notice how it shifted or changed, okay? The only thing that happened based off of that vertical translation was that it all shifted down 1 unit. So there's a key difference between an amplitude change and a vertical translation. An amplitude change physically is going to affect the highest and lowest points of your graph, or your max and your min. It's going to press them up to a higher point. While your vertical translation affects all the coordinates in your graph, it physically is going to move it up or down. Okay? Now, when you're doing these problems, you always have to understand the basic idea or the first original graph of sine. In this idea, sine of x is there because, or excuse me, the reason I use sine of x at the beginning is because I can describe all the coordinates based off of this. But knowing this graph over at least one period is going to be key. Now, let's start to build up with some of the complexity. All right. A lot of these problems, the complexity derives from when I have to actually shift it left or right, or when I have a different period. Okay. So the problem like this, I want to kind of focus on two specific things. All right. How can I change it based off what I see? What is my amplitude, finding all my values, and then always affecting that based off of my original function. For example, use the original cosine function to help you derive this problem. So before I even start, let's actually get that original cosine function. So if we remember, cosine actually starts at starts at 1, and we build off that. So it's going to start at +1, go down to pi over 2, eventually it reaches pi, and then works its way back up. Give me a graph that looks similar to this. Okay, this is my original cosine of x. Well, now, based off the information, let's talk about what we have. So if my equation is y equals the amplitude times cosine bx minus c plus d. In this case, we do not have an amplitude or a vertical translation. We have that b value, which helps us find the period, and we have that phase shift or that c value, which makes it go left or right. So right off the bat, let's make an easy one. Oops. Because it's plus pi over 2, we always know that left and right's always opposite. So it's going to make it go left pi over 2. And then the b value, which helps describe my period, is always going to be 2 pi divided by whatever b is. In this case, it's 2. So in this case, my period is just a value of pi. Okay? Now, when I'm graphing it, we have to understand that really all this is going to do is condense these coordinates. So if we start off by focusing on just the period change. So let's just say I want to focus on just that period change, y equals cosine of 2x. Let's say I don't have to worry about the phase shift yet. I want to understand that this coordinate here now has to be placed at where pi is at. Okay, it's not going to physically move this graph left or right. It's going to condense it closer together. So that if I start at this original point, I should have a point right there where it's also the maximum, or where I repeat my coordinates once again. What does this mean for our graph? How do I actually graph it out based off that information? Well, what I'm going to do is break it down into 3 other coordinates in between my original and my value here. Okay? Or in other words, I'm going to break it up in fourths. Okay? That's the easiest way to remember this, is I'm going to break this value up in fourths. The idea behind it is, notice how in this value we always go up by pi over 2. Well, as I condense it down, I always want 4 particular coordinates based off that period. So if my period starts at 2 pi, I want to find 4 other coordinates to build off of that. Well, in this case, my value is just going to be pi. So what I'm going to do is I'm going to change this and actually write out these other values. Pi over 4, 3 pi over 4, and obviously this value here is 0. So you notice how there are a total of 5 different coordinates from 1, 2, 3, 4, 5? Well, by marking my new period and by breaking it down up until I get to my original point, notice I've created 5 total coordinates for myself. 1, 2, 3, 4, 5. Okay? The reason this is important is because this is kind of an easy way to detail where these values are going to go. For example here, if I know my original coordinates here and my period's at pi now, these 3 coordinates here will just fall in line in a more condensed version. So that next value next to it will just be sitting right there. That -1 that was originally at pi now gets pushed back a complete half of it, or at pi over 2. The pi over 2 value that was originally at 0, or this one, if you divide that by 2 or split it up, it's at pi over 4, giving me a graph that currently looks like this. Notice how it shrunk my period, so now it repeats sooner. It doesn't take the full 2 pi to get there. It repeated at a faster pace. Now, last but not least, we do have to consider our phase shift. If I clone one of these, the last thing we have to consider based off of the graph we currently have is we have to also apply a phase shift to this problem. So if I rewrite the original function, which is 2x plus pi over 2, we have 2 y equals cosine of 2x plus pi over 2. Currently, we have this graph here, which is a description of just that 2 value, cosine of 2x. But now in this last one, I have to apply this left pi over 2 motion. The key thing we have to understand is that this is physically going to shift all of these coordinates over by pi over 2. So if I just take this particular graph I have right here, I'm going to shift it over based on what I currently have. So for example, this coordinate has to shift left by pi over 2. Meaning on this graph, that original coordinate, that starting point, is now going to start here. Pi over 4 is going to shift over, divided by pi over 2. That becomes negative pi over 4. Pi over 2, this original coordinate here, I'm going to move it left by pi over 2, which brings me back to 0. 3 pi over 4, I'm going to subtract by pi over 2 or move it left 2 units to bring me at pi over 4. And then originally, my final coordinate, which was at pi, I'm going to move it left by pi over 2, giving me the new graph right here. This here is one period of cosine, all right, where I have a new starting point at negative pi over 2. Period goes a total value of 1 pi. And the phase shift of pi over 2 shifted it left to that value. Okay? So what I can tell you with these particular problems is that we want to take our time with them. We do not want to rush through and try to jump right to the final graph. Start with your original function and build off of it. Okay? Notice how I take the original cosine graph, I apply any period or amplitude, and then I start applying phase shifts, left, right, up, and down. For graphs like this, I apply my original amplitude, and then I start applying its vertical translation. In this case, it went down 1, so I went step by step, started with sine, applied the amplitude, and then shifted it down 1 unit. Okay? We'll be going over these in class tomorrow, as well as the rest of the week. If you have any questions during the class, and we will talk about them. Besides that, have a great day.